Assalamualaikum. In the last video, I already explained about time and frequency representation that are related to each other. So, basically in the time domain and also frequency domain, when we see on the signal representation, is actually connected and related. And in terms of these figures, I already explained it in the last video. But how about when we want to relate it based on mathematical equation? So in the next slide here, alright, this is how we can convert from a time domain function to the frequency domain function. So how we can convert to each other is by having it to be used Laplace. So Laplace will transform or convert the time domain function xt to be a new function in frequency domain xs using Laplace transform. And this is for the input. Alright, and for the system, we also can convert from the time domain function to the frequency domain function by using also the Laplace. And when we have the output of the system in frequency domain, we also can convert it back to the time domain by using inverse Laplace. So for the Laplace in this course, you will be learned in chapter 4. So I don't want to touch so much on this because you will learn further in chapter 4 later on. And next is the elementary signal, or certain book call it as basic signal. So there are, here I put it as 8 type of elementary signals, and I will explain one by one in this video. First is the unit step function. Alright, the unit step function, or mostly we use it as UT, also known as Heaviside unit function. And this is actually the unit step using continuous time version. And we also can make it as discrete time version of unit step by having it to be U and using N. So N is the unit sample. And if we want, this one is the discrete time. Okay, so the unit step, if you can see on the figure, is actually a function that show that within certain area what is the amplitude. Alright, so this is the amplitude of the function. Okay, and this, if you see over here, there are two conditions of amplitude, whereby the zero amplitude will be when you have t less than 0. Sorry, so this is the area that t is less than 0, and when you have the t more than 0, the amplitude is actually at the value 1 position. Okay, that is unit step function. Next is unit impulse function. So unit impulse function is the derivative. Okay, kalau dalam bahasa Melayu kita sebut perbezaan of the unit step function. So it also known as direct delta function, because when we do the differentiation of the unit step function, we will always use delta, and this is the direct delta symbol. We use the direct delta symbol to represent these functions. That's why the name is direct delta function. And the unit impulse delta t is 0 anywhere except when t equal to 0. So every time we say about unit impulse function, this is the condition that you need to remember. Alright, so whenever the t is equal to 0, alright, it can be anywhere and anywhere of the amplitude. Okay, but whenever what we call it, at the different time than 0, the amplitude should be 0. Okay, so only whenever the time is equal to 0, then it has some sort of value in terms of amplitude. But the rest of the time or period, you don't have any value that represent the amplitude. That's the unit impulse function. Okay, and for unit impulse function, you need to use delta symbol here to represent that the function is actually unit impulse. Right. There are one more thing, what we call as unit ramp function, because this is what we call as differentiation. The unit ramp function will use the integral of unit step function. I will explain it in a bit later. Okay, so next is the sinusoid. I think sinusoid I already explained quite detailed in my course in other course, communication system design, that you have attended last time. So I hope that you still remember. So the general expression of sinusoid, either you use a sine or a cos with amplitude. Okay, and then we have the angular frequency that we can convert it to be 2 pi f t. Alright, f is the frequency, and also the theta to explain about the phase. Alright, if your signal is started from 0, that means there is no phase involved and you don't have to put any phase. But if your sinusoidal signal is starting other than origin or 0, then you may have the phase value over here. Okay, so this one I don't want to explain detail because you already learned it in my communication class before. If you don't remember, please refer back to your notes, or maybe you can find my YouTube channel to refresh your knowledge about sinusoidal in chapter 4. Okay, next is about complex exponential signal. Alright, so this signal use the x and three-dimensional x, y, and z, but the x and y actually use the cosinus and sinus function based on the length r. Okay, so if we take the z is actually the combination or summation of x and y, whereby it's actually using this equation. So this equation with j. Right. So this j is actually what we call as imaginary value. Okay. Certain part using I, but here is actually using J. So when we want to get the R value, alright, we need to go using this equation, alright, and find what is the length of the side over here. Okay, and using this equation actually, we can get the complex or relate to the complex exponential by using Euler's formula. So this Euler formula is using this part, which A times exponential J times theta. So when we use this Euler formula, okay, and expand it, it will be A times with the real part plus with imaginary part. Alright, and the theta is actually this equation. Alright, omega not t plus theta. Okay, so based on this equation or complex exponential signal, I want you to try this example 4, how you can expand the zt function over here, 20ej 2 pi 40t minus 0.4 pi. So if we actually this is example, but it's already giving you the answer. So try to understand the step by step conversion between this line to this line, this line to this line, and this line to this line. Okay, it's just that when you have and for this part you need to use Euler's. Okay, and from this part to I think to this part, because we want to make this equation have cos and sine, and you want to convert to be using the same trigonometry function, so you want to use cos and cos. So in order for you to make this conversion easier, you need to refer to the trigonometry identities, whereby this one will be the one that you need to use in the conversion. Okay, later on maybe I can explain in my online class with you. Okay, this is the unit ramp. Just now we learned about unit impulse function. So for the unit impulse function, it's actually the differentiation or derivative of unit step function. But in the unit ramp, we use the integration or integral of the unit step function. So by having this, alright, actually the definition is we can have this function to be unit ramp. We can convert this unit step function to be unit ramp. So how you can do that is by using the integral equation over here, and as a result you will get this RT equal t whenever the t more than 0 and 0 when the t is less than 0. Alright, so another one way to represent the ramp unit ramp is by having the RT times t times unit unit step. Okay, this one. Okay, next is the sink function. Alright, I think you have seen this type of function before, in terms of when you have the power of a signal. So this area of sink sink X is actually the area that cover below the signal. Okay, and the sink here I can be represented using this equation. Alright, so this is one type of function that you may find as a signal as well. Another one is what we call as rectangle function. This is very famous. You will see this type of function or signal, especially using binary signal, alright, or digital signal. Both are the same thing. Okay, so this function actually work as a switch to turn on or turn off any equipment in specific time period. So in electrical or electronics, whenever you use a switch, especially in digital system, you may have this type of signal to be represented, and how you can make it on and off is based on how the system that you design. Okay, whenever it's on, it maybe the amplitude will become 1, and when you want to switch it off, the amplitude will be 0. So 0 over here, sorry. Okay, so the rectangular function, especially on this figure, alright, can be represented by having the rectangular t equal to 1. Okay, 1 is actually here. So what is the time? the time taken is between negative half t, right here, until positive half t. Okay, and the rest of the area will be 0. Right, so we can put t less than negative half or t more than half here. Alright, but you also can use as others t. Okay, it can be understood as well. Okay, and next is the triangle function. Okay, if you have tried to use the function generator, I think you also know this type of signal that can be generated. Okay, so for the triangle, okay, we use try with the time domain t, right? And if you see on the graph over here, the amplitude will be 1, alright, at 0 origin here, and 0 from negative 1 and below, right? T less than half, and will be 0 when t more than 1. Sorry, this is not negative half, negative 1, this is positive 1. Okay, so when you want to represent it as equation, so you can put 1 minus modulus t or magnitude t, and when the magnitude t is less than 1, you can have it that way, and it will be 0 when it actually modulus t more than 1. So if the modulus t over here is actually when you have modulus negative 1, and it will be positive 1 as well. Alright, so it's either way. This also modulus t, and this also is the modulus t. Okay, that is triangle function. Right, next is the signum function. So for signum function, it's actually this is the derivation of signum function using unit step function on this part. But when we want to translate from this graph or function to the equation, you need to make it and see it properly on the time domain. So for the signum function, right, it's actually 1 whenever this is 0, whenever the t is more than positive, right? When t is actually positive side, the amplitude is 0, right? And whenever the t is less than 0, the amplitude will be negative 1. So it fulfill this one. And every time the t equal to 0, okay, the amplitude is actually 0. Okay, so even though if you see here, why is 0 actually? Because we have negative 1 plus 1. Alright, why this is a 0? Because we have the highest amplitude is 1. Sorry, negative is actually should be negative 1 plus 1. Alright, because the signal should be towards time from negative to positive in terms of time. So negative 1 plus 1 is equal to 0. Okay, and using this signum function, you can have the derivation or differentiation to convert it to be using unit step function. So for this signum t, alright, we have negative 1 plus 2 ut, and when you try to make it both side having unit step, you can convert it to be this way. Okay, so yeah, and we also have this illustration to explain about common function. So we can, this is a way that we can remember when we have this kind of function, what happened actually with the body. Okay, and hands, not body, our hands. Alright, so try to see, because for the sine x, alright, we have this type of equation, and for the cos, so this is the 0 lah. So for the cos we have like this, okay, and for the tan x, tangent x, we have like this, and for the cotangent is the inverse of tangent, we got like this. X is, yeah, if x is the this way, alright, and if you have quadratic x, you have this shape of graph or function, alright, and if you have x and y that have been squared and sum and addition, we will have about this one, circle. Alright, so that is how we try to remember. I mean, during my school time, I always do like this to still remember what the shape should be based on the equation I had. Right, so this is the some of the function that illustrated by the cartoon. Alright, so yeah, try to see each one of it, and if you can, please remember the shape of the function lah, so that whenever you are given this function, you know what will be the shape of graph. Okay, and yeah. So next is about signal operation.